Hi everybody, this is our lecture on section 2.2, volumes by perpendicular slicing. So as with section 1.2, remember by definition the integral from a to b of fx dx is equal to the limit as n goes to infinity, sum I equals 1 to n, fxi delta x, where delta x is b minus a over n, and xi is a plus I delta x. Alright, so now we're going to apply, so in section 2.1 we applied this definition of the integral to calculate areas other than the standard area, although it wasn't really too much different than what we had before with the standard area measurement for the integral. So now we're going to do something different. We're going to calculate volumes using integration. Okay, so here's the basic idea. For volume calculations, using perpendicular slices. So consider a three-dimensional solid object. Which is lined up along an x-axis. For a less than or equal to x, less than or equal to b. So the picture in your mind should be something of this sort. So you've got some three-dimensional object, like so, and it's lined up along an x-axis, which I will draw in a moment. And the slices don't have to be circular. I'm drawing all of them in a circular fashion. They certainly don't have to be. So here's the x-axis, and the solid starts at x equal to a and ends at x equal to b. Now, suppose that at any particular x coordinate, so for any particular x in the closed interval from a to b, the slice of the solid perpendicular to the x-axis at x has area a of x. So the picture to have in your mind is as follows. Alright, so at a given x coordinate, say right here, so at this given x coordinate, here is the slice of the solid perpendicular to the x-axis. and say the area of the perpendicular slice is a of x, meaning a function in terms of x. So the area of that slice is a of x. So this is the main challenge in using this this method. Okay, is figuring out what a of x is. Okay, that's the main challenge using this method. So we're going to go over lots of different examples and determine what this a of x is. But once you know what a of x is, a function of x that measures the area of this slice, now what you can do is we will estimate the volume of the solids by thickening these areas into slices of thickness delta x equal to b minus a over n. Okay, so the picture to have in your mind now is the following. Well, actually, you don't necessarily have to have it in your mind from now on, but just for now, just for the sake of this discussion.
I can learn to understand you much better if I can get familiar with the way you talk.
Okay, we learned that's your opinion. All right. So you've got, so A is equal to x0, and then this is x1, and then this is x2, x3, x4, x5, x6, x7, say. Right, where here, delta x, which is the distance between those things, is b minus a over n, and xi is a plus I times delta x. So here are all of these slices, like that. So that's the slice at x1, at x2, x3, x4, x6, and x7. And then you thicken that slice into something with thickness delta x. Like that. So you get this kind of cylindrical thing. Not that it necessarily has to be round. It certainly doesn't have to be. Then this one's going to be smaller. This one is slightly bigger. Oops. This one is a little slightly bigger. This one is moved down. And this one is just, has zero volume like that. Okay, so you've got these thick slices, and the thick slices, so the volume of the thick slice is, well, so you've got this area AX, AXI, so this is at XI, and then you thicken it just by extending sideways into this thick slice of thickness delta x. All right, so this is at xi, so the area is equal to delta x times the area AXI. All right, so this right here as area AXI, and then you thicken it like that, delta x. So that's a standard sort of thing with volumes, right? If you have a two-dimensional object with a certain area, and then you just sort of extend it in one direction, then the volume is the area times the thickness. So that's the volume of each one of those, block slices, thick slices. So now the volume of all thick slices together is the sum I equals 1 to n of the thickness times, the area times the thickness of each slice, the volume of each slice, AXI delta x. The more thick slices you have, the better the estimate of the volume, right? This estimates the volume, these blue thick slices. It estimates the volume of the black solid, right? And the thinner and more numerous those slices become, the better the estimate gets. Therefore, the actual volume is the limit, as n goes to infinity, of this Riemann sum. The more slices there are, the better and better the estimate of the volume becomes. Therefore, the actual volume is the limit as n goes to infinity. The sum I equals 1 to n a x I delta x, which by definition is the integral from a to b of this function, ax delta or dx. Right, so we are interpreting the integral as a volume measurement, no longer an area measurement. Okay, so in summary, okay, let's look at it very carefully. You've got your solid, and it's lined up along an x-axis from A to B. The area of a perpendicular slice, okay, if you can express it as a function, a of x, just x, not any other variable. If you can express it as a function, a of x, then the volume is just the integral of that area function. All right? All right. So in summary, given slices of area, perpendicular slices, of area AX, volume is equal to the integral from A to B of the area function. That's it. Okay, that's the whole idea. All right. So let's take an example. So the base of a solid is a circle of radius what, 3. The base of a solid is a circle of radius 3. Perpendicular cross sections, so slices perpendicular to a diameter of this circle are squares. What is the volume of the solid? Okay? I'm not going to draw what this thing looks like. Okay? I'm not interested in what the thing looks like, really. All I'm interested in is what the area of the perpendicular slices are. And I've been told, or I'm telling you, that the perpendicular slices are squares. And the base of this guy is a circle. Okay? So let's take a look at that circle. So here's the base of the solid. It's a circle. Right, and the circle is given by what equates? Circle of radius 3. And the circle is given by the equation x squared plus y squared equal to 9. In other words, y is equal to plus or minus, well, the upper half of the circle is y is equal to the square root 9 minus x squared. That's for the upper half of the circle. The lower half of the circle is y equal to the negative of 9 minus x squared. Okay, here's the diameter where the perpendicular slices are squares. I just picked that to be the diameter lined up along the x-axis. So the slice perpendicular to this, okay, is a square. So there it is. It's not the whole square. That's just the base of the square. All right, this blue line is the base of the square slice perpendicular to the x-axis. What is the length of this blue line? The length of the blue line is, well, what's this length? Right, this length here is the distance from here to the y-coordinate. So the length is that. And this length here is the same. Right, so the length of that blue line is 2 square root 9 minus x squared. So what is the area of the slice? So that blue line is one side of the square. So the square is coming out of the paper here. That's the base of the square, and then the rest of the square is like here. Let me try another hand at that. But I'm not going to draw it just because it's going to look, it just looks awkward trying to draw it like that. Right? So the square is going straight up and down. Right? And that's just one side of it. We don't need to see the whole thing. I mean, we know that the area of the square is the length of one side squared. Right? So the area of this square, should make this black actually. The area of this square is a of x, which is equal to 2 square root 9 minus x squared. That's the length of one side, squared. So I got 4 times 9, so it's 36 minus 4x squared. So that's the area of the square at x. This is the x coordinate right here. All right, so the volume of the solid is the integral of the area. Okay? What are the limits on the integral? From where to where? Well, just take a look. It's from minus 3 to 3. All right? From minus 3 to 3. So it's the integral from minus 3 to 3 of the area, ax. So integral from minus 3 to 3, 36 minus 4x squared. So that's 36x minus 4/3, x to the third, from minus 3 to 3. So this is equal to 36 times 3. Let's see, get my calculator. $216 minus 4/3, so 8/3 times 27, so it's 8 times 9 is 72. So that's 216 minus 72, 144. Okay? So that example uses precisely the definition. Okay, I've got a solid, and I just determined what the slices are, and it tells me what those slices are shaped like. I determine the area of that slice. So this is the base of that solid. This is the slice perpendicular. That's one side of the slice perpendicular to that base, and it's a square. So it's one side of a square. The length of it, well, the length of the line from the x-axis to the curve is the function. The distance from the x-axis to the curve is the function that defines that curve. So this distance is square root 9 minus x squared, so this distance is the same, so the distance is twice that. Twice times root 9 minus x squared, so the area is that squared, which is this. Okay? All right. How about this? A pyramid has a, let's say a square bottom, right, like the pyramids in Egypt. Has a square bottom with side length 200 feet. Okay? The height of the pyramid up in the center is 100 feet. What is the volume of the pyramid? All right, so let's draw a picture. So here's the base of this pyramid, and here's the top. Let me see. Okay. So there it is. All right. So what I'm going to do, and then here's the top, and it's right over the center of the square bottom, like that. So that's a right angle there. All right, what I'm going to do is I'm going to make that the axis along which I line up the solid. Okay, this length is 200 feet, and this length right here is 100 feet. And this length right here is 200 feet. I'll leave out the FT. This length right here is 100. There we go. All right. So I'm going to make this the axis along which I line this guy up. So I'm going to make this zero. Now I'm going to make this point 100. And then it goes on from there. All right, this is 0, this is 100, and then here is some value x. And now I'm going to slice this guy perpendicular to that. So what kind of slice do I get? Well, it's going to be another square, yeah? That didn't turn out to be very square looking, did it? Let me try that again. That side is off by quite a bit. All right, close enough. So there's my slice through the X there. Okay, and that slice is a square. We need to know what the side length of that square is. Okay, so let's take a look. Within this picture, what color should I use here? Within this picture here, let me draw another one. Within this picture here, notice we've got this triangle. Okay, and here's X, and here's this line right here. So let's pull that triangle out. This is point 0, this is point X, this is point 100. This length down here is what? Well, the entire length here is 200. And therefore, the purple length here is 100. It's half of that, right? So down here, we have length 100. So I guess it should be more square, like that. And now we have this length right here is what we're interested in. Right? And that length right there is half the width of that blue triangle. So let's give that blue triangle sides of width W. All right, so W is the width of the square slice. So right here is W. Oops. So at X, there's W. So we need to know what W is in turn, or sorry, that's half of W. That's half of W. So we need to know W in terms of X. So let's write W over 2. What is this W in terms of X? And then we can square it to get the area of that square. Okay, well, we set up a ratio using similar triangles. 100 over 100. All right, this length here is 100. This length here is 100. So 100 over 100, so using similar triangles, (100 over 100) is equal to X over W over 2. Right? So W is going to be equal to half of X. So W over 2 is equal to X. So W is 2X. Right? So W is 2X. Therefore, the area AX is equal to W squared is 4X squared. So now what's the volume of the pyramid? What's the volume of the pyramid? Right? We've got this slice of width W, and we've determined that the width W is 2X. So that square slice of width W with W equal to 2X has area in terms of X as 4X squared. 2X quantity squared, which is 4X squared. Okay, so what's the volume? So the volume is the integral of the area. Oops. Come on. Oh, you did that. View actual page layout, one page continuous. There it is. So the volume of the pyramid is the integral from 0 to 100. Right, we're going from 0 up here down to 100 down here of a of x dx. So it's integral from 0 to 100 4x squared dx is equal to 4/3 x to the third from 0 to 100. So that's equal to, so that's 10 squared, 10 to the 6th, 4 million over 3. So 100, 100, 100. Yes, okay. All right. So none of the problems in this section actually are too easy. They're all, pretty involved. I mean, we're doing something actually that's quite sophisticated here. Pretty sophisticated applications of integration. You're definitely going to need some practice to, to really solidify this material in your mind. Okay, but let's just keep going with it. All right. Oh yeah. Okay. All right. So the next situation is solids of revolution. Well, solids obtained by revolution, not solids that revolt. So the basic setup is this. So given a function y equals f of x, continuous function, y equals f of x for a less than or equal to x less than or equal to b. Okay, I want to rotate this curve around the x-axis and measure the volume of the resulting solid. Okay. So here's a picture of what I'm talking about. Here's your xy axis, and I've got this function f of x, and we'll say that it's bigger than or equal to 0. I guess it doesn't have to be. Let's forget about that. Like that. So I'm going to take this guy and I'm going to revolve him. So here's A and here's B. I'm going to take this guy and revolve him around the x-axis. And what I get, right, is a solid that looks like this. And the cross sections of this solid perpendicular to the x-axis are just disks. Right, cross sections perpendicular to the x-axis are disks. All right, so here at xi, the disk has radius what? What's the radius of that disk? Well, what's the curve there? The radius is the distance from here to here. Right, and this is the curve, I didn't label it, but this is the curve y equals f of x. So this radius is just fxi. Our disks, where the disk at xi has radius fxi. So the area at x is equal to, well, pi times the radius squared, fxi quantity squared. Right, so the volume is equal to, well, it's the integral from a to b of pi fx squared dx. It's just the area of those slices. All right, and can you think of any interesting examples that you might like to try? Can you think of any examples you might like to try? Well, let's calculate the volume of a sphere. I mean, we know, maybe you know, that the volume of the sphere of radius k is 4/3 pi, 4 pi over 3 times k to the third. Okay, but we can confirm that. Okay, so take the 1/4 circle of radius k in the first quadrant. Okay, so that is this. And the equation for it is y is equal to k squared minus x squared. Square root k squared minus x squared. This doesn't look circle, does it? There we go. Oops. That looks a little better. Or maybe not really, but if we revolve this around the x-axis, gives us half of the sphere of radius k. Right, so right. So now we can get the volume of the whole sphere just by calculating this volume and multiplying by 2. Right, so at xi, we have a slice that is a disk. Right, so we have this slice that is a disk here. That's solid back there. So the slice at, oh, and this is k. So the slice at xi has radius, well, it's just the distance from here to here. And then this is y is equal to k squared minus x squared. So that's the radius. K squared minus xi squared. So the area at xi is going to be equal to this thing squared. K squared minus xi quantity squared. So the volume of the whole sphere of radius k is equal to, well, twice the volume of the half sphere. So that's the integral from 0 to k of the area function, k squared minus x squared dx. So antiderivative is k squared x minus 1/3 x to the third from 0 to k. So this is k to the third minus 1/3 k to the third. Yeah. Oh, I'm sorry. Pi times, I lost my pi somewhere. Yeah, there's the pi. I didn't put a pi. I knew something's missing. So the area is pi times k squared minus xi squared. So this is 2 pi. 2 pi. 2 pi. Right, so the area of a circle is pi times the radius squared. From 0 to t, so that's 2 pi times k to the third minus 1/3 k to the third. So that's 2/3 k to the third. So we have 4/3 pi k to the third. So that is the volume of a sphere of radius k. And, you know, perhaps you knew that formula already, but, you know, there's a proof that the formula is actually correct. Okay? Let's see, how long is the video? All right. There is one more topic. If you want to watch this video in stages, you can. But I want to get the entire lecture for the section in. So that's the sort of basic setup for revolving curves. So you have your function y equals f of x, like that, and you revolve it around the x-axis. But you don't have to have just that. There's something definitely more general that follows the same idea. So revolving more general regions around an axis. Okay, so consider a region enclosed by two curves by, so just like we had in section 2.1, so a region caught between two curves, G over F. So here's the G, and there's F. So that's G of X on top, F of X underneath, and that is from A to B. Consider a horizontal axis, so not necessarily the x-axis. Consider a horizontal axis at y equal to k. So if this is k, here's that axis. And what we want to do is we want to revolve that region around this axis to obtain a solid and then measure its area. So revolve the region around the axis y equals k and measure the volume of the resulting solid. One moment. So here's the picture. I'm not going to draw the whole solid because it becomes kind of messy. And what I'm going to do also, I'm going to erase the x-axis here. So I just have this so here's the y-axis. The x-axis is missing. Well, it's there, I'm just not showing it. And here's the horizontal line, y equal to k. So the x-axis is y equal to 0. And I'm going to take this solid and revolve it. What does the cross-section look like? So a cross-section at x is going to look like this. See that? Yeah, that's a nice way to draw it. All right, so the cross-section perpendicular to at x perpendicular to the line y equals k as well as a washer shape. It's called an annulus, i.e., a washer shape. Right, a circle with the hole in the middle popped out. Circular hole in the middle popped out. All right, well, what is the area of that? Okay, what's the area of that slice? Not as complicated as it might look. Oops. All right. So if you've got two concentric circles like that, and here's the center, right? You've got a small radius, little r we'll call it, and you got a larger radius, big R. Right? And the area here, well, it's the area of the big circle minus the area of the big disk minus the area of the little disk, right? Right, so the area is equal to pi big disk minus pi r squared for the little disk. Okay, well, what is it here? So here, the little radius is f. Well, let me see. So in this picture, well, let's just use this, I guess. In this picture here is equal to pi. Well, the large radius is the distance from here to here. Right? It's g minus k. Y equal to g. So let's put those in there. Y equal to g of x. Y equal to f of x. Y equal to k. Right? So the large radius is g, y equal to g, minus y equal to k. And the little radius is y equal to f minus y equal to k. And that's it. Y equal to y equal to g minus y equal to k. Y equal to f, y equal to k, minus y equal to k. So the area is pi times gx minus k squared. By the way, this is if the axis is underneath the region. If it's above the region, and then it's the absolute value of this. Just to keep it positive. All right, minus pi times little f minus k squared, like that. So the volume is equal to pi times the integral from a to b gx minus k squared minus fx minus k squared dx. All right, so let's do a quick example of that. Okay, we're almost at an hour. So here's my region. So I'm going to have y equals x squared y equals x squared, and then the line y equals x. Okay, and I'm gonna revolve this thing, and let's put the axis up here around the line y equals 2, and this is the point 1, 1, and here's the line y equals 2. All right. So the little radius in this case is here. That's the little radius, or sorry, the little radius. And the big radius is here. All right, the little radius is the distance from here to here. Big radius is distance from here to here. So the little radius is 2 minus x. And the big radius is 2 minus x squared. If this axis of rotation was underneath, it would be x minus, the -1, and or x squared minus -1. But I mean, whatever the case might be, it's larger minus smaller. Right? So 2 is larger, x is smaller, and then 2 is larger, x squared is smaller. So little radius is the shorter distance, and big radius is the bigger distance. So 2 minus x for the little radius, 2 minus x squared for the big radius. So the volume is equal to integral from 0 to 1 pi times the big radius squared minus the little radius squared dx. So that is equal to, so what you want to do is multiply out this whole thing here. So we got x to the 4th minus 4x squared plus 4 minus x squared minus 4x plus 4. So this is equal to x to the 4th minus 4x squared minus 5x squared plus 4x. X to the 4th minus 5x squared plus 4x, and then plus 4 minus 4, so those go away. So antiderivative is 1/5 x to the 5th minus 5/3 x to the 3rd plus 2x squared from 0 to 1. So that's 1/5 minus 5/3 plus 2. So that's 3 minus 25 plus 30 over 15. So this is equal to 33 minus 25, 8 over 15. So that's the volume of that solid there. Okay, so we've got several techniques for calculating volumes with solids, of solids by these perpendicular slices. We've gone through several examples, and all of them amount to the same thing. Okay, you've got your solid lined up along the x-axis, along an x-axis, or a t-axis, or whatever have you. Where is it? You've got your solid lined up along the axis from A to B. From A to B, here's your solid. And then the slice at x has the area AX. And then the volume is just the integral from A to B of AX. Actually, let me put that picture underneath there. So the whole challenge in applying this is to find that area function AX. Is setting this guy up along an axis and then figuring out what that area function is. Okay, All right, so that's it for this lecture.